Hi everyone, my name is Gabriel Loyer. I'm a master's student at the Université du Québec à Montréal, and I was supervised by Vladimir Reynards. And I'll talk with you about the integer programming framework for simultaneous prediction of RNA structure with pseudoknot and insertion of local 3D motifs. So our main motivation is that the structural motifs in the loop are essential for the final shape of the molecule, enabling its multiple function. However, accurate 3D structure is also limited for interaction that form inside those loops, and the prediction of RNA structure canonical base pair from a single sequence, especially pseudoknot one, remain challenging. Originally, we had a tool called iRNA, which do motif insertion to find the best possible suited secondary structure. And in those motifs, we have non-canonical interaction, which we have all the type here, which are really important for the construction of the 3D structure. So using a database of those motifs with their interaction, we find the possible insertion point of them, and we use integer programming to find the best possible motif that will maximize the sum of the square length of the motif that we inserted. Another tool that we will look towards, it will be RNA-fold, which is pretty popular for good coverage of well-predicted base pairing, and it's also returned us a nice base pair probability matrix. However, it does not predict the presence of pseudoknot pairing, as well as our first iteration of our tool. So if we have, like, for example, 2TPK, which has a multiple pseudoknot interaction, they will not be covered in our program and also in RNA-fold because they don't have representation of pseudoknot in their thermodynamics model. However, for the case of RNA-MYP, we find a more suited hairpin since we partially found the hairpin motif here. So my work was to find a fix for those limitations for the pseudoknot one, and also we wanted to avoid providing an initial secondary structure for the RNA-MYP tool. The main goal was to help guide the insertion of the motif, and afterwards see which pair we need to be removed to have the most suited secondary structure. So to fix those limitations, we use a concept coming from a tool called IPNOT, which is the base pairing decomposition, as well as still using motifs. So the main goal is to have a pseudoknot structure and to decompose it into multiple pseudoknot-free substructure, where each substructure of a specific level will have all this pairing crossing at least one pairing from the level below it. So here we have two pairing at level 2 that will cross at least one pairing in level 1, and in level 1 there will be no crossing in the substructure, and there will also be the motif inserted as well. What's enabling us to do is that we can now use RNA-fold to calculate the base probability matrix of those pseudoknot-free substructure, and we will sum them together for all of the substructure to have a global approximation of a base pair probability matrix of the sequence. So the main goal of the pairing decomposition will be to maximize the sum of the probability of the base pair that we inserted, and we will combine that objective with the motif insertion objective to have a global objective function. We also retain another algorithm from the RPNOT, which is the iteration part. So once we provide a secondary structure, we will then refeed it to our input to help to put actually constraint on the base pair probability for RNA-fold. And we will repeat the convention, the iteration until there's a conversion or maximum of iteration. So here is an example of only using the base pairing decomposition. Since we want to maximize the base pairing probability inserted, there will be a lot of base pairing inserted. And however, if we combine them with the motif insertion, we can see that the motif still retain the shape of the hairpin, but also partially found the presence of the pseudoknot. So overall, we benchmark our tool on all non-redundant RNA below 150 nucleotide that add at least one pseudoknot, and we use metric of the PPV, sensitivity, and F1 score. We compare the result against RNA-fold, against an implementation of only using base pairing decomposition, and an implementation of only using motif insertion, and also a hybrid approach. All of that was managed using a weight of those two objectives. And we found out that using a hybrid approach with a weight of 0.1 yield the best result. If we look closer for the PPV, so how many of the pairing that we predict are actually in the known structure. For an RNA fold and the motif insertion algorithm, there is a good score, but they will never predict correctly the pseudoknot interaction. And for the base pairing decomposition, since it gave a lot of base pairing, the score will be lower. But once we combine them together, we still give a good result. For the sensitivity, so how many of the known structure do we actually predict correctly? We can see that the base pairing decomposition is good at that because it predicts a lot of base pair. But when we combine the two approach of the motif and base pair decomposition, we still have a good result. And overall in the F1 score, so the correlation between PPV and sensitivity, we can see that the best approach will remain the weight of 0.1. It's also an approach that predicts well the canonical and wobble pair at the location where the motifs are inserted. For the pseudoknot count, so we found out that with this way, there's approximately half of the time we correctly predict the presence of the pseudoknot at the correct level. And we can also see that the more we tend toward the motif insertion, the more challenging it is for the IP solver to find an optimal solution in time, since we find we fix a time limit at around 15 minutes. So in conclusion, we want to update the motif database using Carnival to have a more detailed interaction and to have a better and bigger catalog. And also we want to use base pairing insertion instead of using direct matching of the sequence for the motif insertion. Thank you.